everyone, welcome. My name is Xi Zhen, and on behalf of the lecture committee, I would like to welcome you all to this week's talk in our spring 2025 faculty lecture series. This is our fourth talk in the series, and we have two more coming. So next week, please join us again with Professor Justin Shaddock in philosophy. He will speak about Kant and the problem of happiness. And then we have one more after that. So before I introduce this week's speaker, I would like to share a little anecdote about how the faculty lecture series first started for those first-time attendees. So the faculty lecture series was founded in 1911 by Catherine Mariotti Pratt, the spouse of a faculty member who wanted to, quote unquote, relieve the tedium of long New England winters with an opportunity to hear Williams professors talk about issues that really matters to them. From these lighthearted beginnings, the faculty lecture series has grown to become an important forum for tenured professors to share their latest research with the larger intellectual community of the college. Today, we'll be hearing from Professor Ralph Morrison. Ralph is an associate professor of mathematics in the Department of Mathematics and Statistics at Williams. And after graduating from Williams College in 2010, he received his PhD in mathematics from UC Berkeley in 2015, and then complete a postdoc in KTH in Stockholm before returning to the Purple Valley. And his research includes tropical and algebraic geometry, focusing on tropical curves, and chip firing games on graphs. Please join me welcoming Ralph.
Thanks so much for the warm welcome, Xi Zhen, and thanks everybody for coming out. So throughout this talk, if you have any questions at any point, please, feel free to interrupt. Also happy to answer questions at the end. I should say I am going to have to leave right at 5:30. I have a commitment to some of my junior colleagues, very, very junior colleagues. In particular, I have to go home and feed them dinner. Now, I'm sure all the non-math professors in the audience are a little worried that I'm only getting them into math things like pentagonal tilings and skeletons of four-dimensional polyhedra and what have you. Don't worry, I'm making them branch out into other Div 3 things. For example, they're very, very into biology. And if there are any non-Div 3 professors in the audience, don't worry, we're branching them out in other ways as well. We've been trying to get them into comparative literature. Mostly they're comparing tastes of different books, but baby steps, quite literally. So let's talk about algebraic geometry. So for those of you who haven't played around with algebraic geometry before, looking at this, you might ignore the ick and say, oh, there's algebra and geometry. So certainly there's going to be some algebra running around, maybe some equations, some x's and y's, who knows, maybe even a z thrown in there. And there's going to be some geometry, so maybe shapes, triangles, circles, if they can sneak into the triangle factory, pentagons, hexagons, other gons, maybe some three-dimensional shapes like cones and spheres and homers and all that fun stuff. In algebraic geometry, though, we're going to try to narrow the lens a little bit on both these fronts. I'm not going to look at just any equation, and I'm not just going to look at any shape. In particular, I'm always going to look at shapes that are defined by polynomial equations. What do I mean by a polynomial equation? I mean I have some variables like x and y running around, and I'm allowed to multiply things together, including those variables. Maybe I multiply by some constants. I can add those up, but that's about it. So you're allowed to multiply variables together with some coefficients, add them up, and then I always like to set them equal to 0. So for example, x minus 2y plus 1 equals 0. You could rewrite that as like y equals x over 2 plus a half if you wanted to write it in y equals mx plus b form. So that's a polynomial. We set it equal to 0, and we want to think about the shape that it defines. So we're going to have to work in two-dimensional xy space, and so in this whole plane, I'm going to think about every single point that I could have in this plane. I'm going to plug those in, the x-coordinate for x, the y-coordinate for y. If that equation holds, then I'm going to plot that point. If it doesn't hold, I don't plot it. And as many people might know, this is going to give us a line. So the set of points satisfying that relationship is this line. And just to be super duper explicit, the fact that that point 1, 1 is one of the points I drew, that's because if I plugged in x equals 1 and y equals 1, my equation would hold. So that's what I mean when I say starting with a polynomial, looking at the shape it defines. We could get a little more intricate than that if we don't want just a couple of variables added up with some coefficients. For example, we could have x squared plus y squared minus 1 equals 0. You might have seen that more often written as x squared plus y squared equals 1. Algebraic geometers are very nihilistic. We like to take everything and set it equal to 0. We like things to be nothing, I guess. But people might recognize that as the unit circle, set of all points that are distance 1 from the origin. These are the kinds of shapes that we look at in algebraic geometry. Now, a lot of us just kind of take for granted, oh yeah, sure, you have an equation, you have some space, you plot out your points. Of course, this is what we do in middle school and high school algebra and stuff like that. But of course, people had to invent this at some point. So in terms of how far back this goes, having an equation and then plotting stuff out in the plane, a lot of people will give credit to Descartes in La Géométrie. I don't see anyone from Romance languages, so maybe we can figure out the translation of that later. I'm not sure. But anyway, in 1637, he sort of laid out this notion of having a plane, Cartesian plane, that has a nice ring to it, whereby you take these equations and actually think about them geometrically. So a lot of people point to Descartes as being one of the first people to really put that algebra and that geometry kind of on equal footing. He was also the one who set the convention of, hey, x, y, and z, those aren't letters we use very often, let's let them be variables. So we have him to thank for that as well. There's earlier instances of people doing this sort of thing, though, so I'll point to Persian polymath Omar Khayyam, who in Treatise on Algebra in 1079 was solving some, I think, quadratic and cubic equations and things like that, which were purely algebraic, but translated them into a geometric problem. Other people do that sort of thing, but he really laid out, sort of the key essence of algebraic geometry, which is no attention should be paid to the fact that algebra and geometry are different in appearance, sort of really putting them on equal footing. You can find other folks who did similar sorts of things, but I'll point to those two as, people who think about these kinds of things. So far, all our pictures are in 2 dimensions. There's no need to stop at 2 dimensions, though. For example, I see Fajr and maybe a few other folks from my multivariable calculus class in the audience. So we've got all these fun quadric surfaces, so x squared plus y squared plus z squared equals 1 in 3-dimensional space. Now we're plugging in x, y, z coordinates. That defines a sphere. There's an equation defining a paraboloid, an equation defining a cone. You can get more fancy than that if you want. For instance, there's one, if you use some cubes equations, you get that fun red shape over there. I'm not going to try to write that last equation. It involves, x to the 5th and stuff like that. It's a really fun shape. I think it has 31 of those little nodes that come together there, and it's the most possible nodes you could have for an equation of that size. So you can do all sorts of fun stuff. And you can go 4 dimensions, 5 dimensions. It gets harder to draw pictures. We're going to be boring, though. And by boring, I mean incredibly interesting once we unpack all the cool richness behind them, by playing around with plane curves. So we're living in 2-dimensional space, polynomials in 2 variables defining curves. So for example, we've got that line we were looking at before. I've changed my circle now to an ellipse just by changing around my coefficient sum. And there's a more intricate curve that I've got maybe defined by a more intricate polynomial. And just to start attaching some complexity, measure of complexity to these things, I'm going to use a term called degree. So I'm going to say that line is degree 1, that ellipse or that conic is degree 2, and that last curve there is degree 3. That's just referring to the sorts of terms that are allowed to show up in your equation. For example, degree 1, that just means you've got variables by themselves, maybe with some coefficients. That gives you lines and things. Degree 2 means you could have an x squared or a y squared or an x times y. This is getting you shapes like circles and ellipses and hyperbolas. Degree 3, x cubed, x, y squared, that sort of stuff. You can get a little bit more richness there, and you can keep going from there. So we're going to be thinking about stratifying these curves by what their degree is. So let me tell y'all the main theorem we're going to be thinking about today. And the theorem says this following beautiful fact. Let's say I have 2 of these plane algebraic curves, so they're defined by these polynomial equations. And let's say their degrees are c and d. So c and d can be as big as you like. Then those 2 curves are going to intersect in c times d points. So this tells me if I've got these 2 big infinite curves, they're going to intersect each other in a finite number of points. I can count up exactly how many points that is. That's a really nice result. This theorem goes back a really long time. I think the first person who ever articulated it was Isaac Newton. People point to 1687 because I think he cites this just as a fact unproven somewhere in Principia, but he also refers to it earlier in, I think, 1665. So he was maybe the first person who stated it. A little more than a century, or about a century later, you had a French mathematician, Etienne Bézout, who stated this theorem in slightly more generality, and he kind of proved it. It doesn't actually hold up to what we consider to be a proof these days. And as with many, many results in algebraic geometry, it turns out, it wasn't until the 20th century we actually figured out how to prove this in a way that's completely rigorous and didn't involve waving our hands at all. So occasionally people will point to Jean-Pierre Serre, who developed some of the machinery that you need to actually rigorously prove this thing. I think it's his 100th birthday next year, so should be a fun birthday conference. So anyway, long history, didn't really get properly proven until the last century. So who we named this after is a little unclear. Newton, first person who said it. Serre, maybe, gets credit for proving it. So either one of them seems fine. Let's just take the temporal average and named it after Bézout. That seems like a good compromise. I'm being a little tongue-in-cheek. Bézout did a pretty good job proving it. Anyway, that's called Bézout's theorem. That's the big thing we're going to be thinking about today. So I want to show y'all a few concrete manifestations of Bézout's theorem, let's say for some small degrees. So what does Bézout's theorem tell us about some simple curves? It tells us two lines, that's two curves of degree 1 and degree 1, those intersect in a point, because 1 times 1 is 1. And a line and a conic, those are going to intersect in 2 points, because a conic is degree 2, line is degree 1, 2 times 1 is 2. And two conics, say this pair of ellipses right here, those should be intersecting in 4 points, because degree 2 times degree 2 equals 4. Sound reasonable to everybody? Yeah, David.
This is the maximum number of intersections, like two parallel lines don't intersect, right?
You just reminded me, I meant to change the title of this slide. This is actually some examples of blatant lies rather than examples of Bézout's theorem. You also get a certificate for catching a mathematician in a lie, so you can hang on to that there. Congratulations. So absolutely, these things are not true. Some of the time they're true, but not always. For example, two parallel lines. Those don't intersect at all. So Bézout's theorem couldn't possibly be true as we stated it. There's an even weirder thing that could happen. What if you pick the same line twice? The colors are maybe not super visible, but it was a blue line and a red line. What if I pick them at the same time, and it's just a single purple line? Well, that's like infinitely many points of intersection. I didn't say C and D had to be distinct, right? So maybe we throw out that case. But the two parallel lines, that's a problem. We keep getting other problems in these other cases too. For instance, there's a line and a conic that don't intersect at all, or a line and a conic that do intersect, but at exactly 1 point rather than 2. And things get even weirder when you're looking at two conics. For instance, let's say I'm doing circles. There's some circles intersecting in 2 and 1 and 0 points. I can't actually think of how to draw a pair of circles that intersect at 4 points. So it's not just that this isn't always true. It just seems never to be true if I have a pair of circles. So something's horribly, horribly broken in the way that I defined Bézout's theorem. So we're going to have to try to fix that. So that's what I want to spend the next chunk of the talk doing, figuring out how to fill in some of the gaps that maybe we left out to understand these odd cases. Any questions so far before we start trying to repair that theorem? Okay. So maybe we bit off a bit more than we could chew by working in two-dimensional space. It's so many dimensions, so hard to picture. Let's think about algebraic geometry in 1 dimension, algebraic geometry in 1 variable. It turns out some of the issues we were spotting are already going to pop up here. So here's a degree 2 polynomial in 1 variable, ax squared plus bx plus c. A, b, and c are some constants. A is probably not 0, so it's actually degree 2. I'll call that thing f. And as always, I like to set that equal to 0. Now, we learn in middle or high school the quadratic formula, which tells us, oh, I know how to solve the x's that satisfy it. It's negative something plus or minus squared is something divided by something. But let's think about the geometry and the algebra. Some people would call that algebra. That's not algebra. It's not polynomially enough. Anyway, what's going on geometrically? So we're going to cheat a little bit, because technically, if we have 1 variable, we should be thinking 1-dimensionally. The things we want to think about are actually all going to be living on the x-axis. But let's give ourselves an extra dimension so we can visualize things a little bit better. So what we do is we plot out in 2-dimensional space the graph of our function. We think about plugging in every possible value of x, think about what gets spat out. That gives us that parabola there. And we're interested in points like this alpha and this beta, those points where we cross the x-axis. So geometrically, the shape that's defined by that polynomial equation is just a pair of points, alpha and beta, living on that line known as the x-axis. So that's the geometric picture we have. What does that tell us algebraically? It tells us something about how we can factor our polynomial. Turns out that if you have these two roots, alpha and beta, you can take your polynomial and write it as a product of simpler polynomials. Maybe you got some coefficient out front, but from there it's just x minus one of the roots times x minus another root. Root just meaning the points where your polynomial is equal to 0. So that's sort of the nice picture of what's going on for algebraic geometry in 1 variable. But again, things can go wrong. For example, what if there's only 1 root? For example, there's a quadratic equation that's only going to be intersecting the x-axis at a single point. Or what if there's no root? What if there's just no points I plug in that make it equal to 0? That can totally happen. There's explicit examples of that. Well, we have ways of getting around that. It turns out we have to count roots with a certain multiplicity. So this is very hard to actually rigorously define, but the fact that this curve is coming down and barely touching that point, kind of hanging out there for too long before heading back up, that means somehow I need to count that root twice rather than just once. And so it turns out that this polynomial can factor based on its root. It's just I have to have that root showing up more than one time. We also need to do things like work over complex numbers. I need to be allowed to take square roots of -1, maybe not surprising given that the previous slide had a formula where a square root was showing up in it. And in particular, this equation right here, even though I couldn't spot any roots in my real picture, it did factor as long as I was allowed to have complex numbers running around. And indeed, these complex numbers, 1 plus the square root of -1, 1 minus the square root of -1, those are the numbers that make this polynomial equal to 0. So we need to allow for multiplicity. We need to allow complex numbers. Once we do that, all of our theory works beautifully. In particular, there's this great theorem, fundamental theorem of algebra, tells us you got a non-constant polynomial, let's say with some real coefficients, degree n. You can factor it as some constant out front times x minus a root times x minus another root, and so on, where those roots are the complex roots. Some of them are real numbers. Some of them have square roots and negative numbers floating around. And you have to have those appear with certain correct multiplicities. So that's how we fix things in the single variable case. And that's pretty much the whole story there. So let's take those things and try to apply them to Bézout and see what happens. And it turns out that counting with multiplicity and allowing complex numbers does fix a lot of our problems. For example, right here I've got a circle and I've got a line and they just miss each other, right? I'm supposed to see 2 points, I don't see any. Well, it turns out if you're willing to take square roots of negative numbers, you can actually find 2 intersection points. So Bézout's theorem is actually all good for that one. For this sort of picture where you have, say, a line barely touching a circle, again, that's hinting at some kind of multiplicity. Actually defining that multiplicity is very tricky. That's the sort of thing you actually maybe need the mathematician like Sayre to figure out. But it turns out that there is a reasonable way to count that with a multiplicity. Here we count it with multiplicity 2. So there is only 1 point, but it shows up double. And so that matches our formula. However, that doesn't fix all of our problems. In particular, David is still very, very sad because 2 parallel lines still don't intersect. That has nothing to do with the fact that we couldn't take square roots of negative numbers, right? Like, no matter what, you can try to solve them. Square rooting negative numbers doesn't help. And this would take a bit more work to show. Turns out 2 circles never intersect more than twice, even when you're using the complex numbers, which is surprising. You might think, oh yeah, I'm only seeing 2 intersection points there. Surely I'm going to see 2 more when I start being allowed to square root stuff. And it turns out, no. That doesn't get fixed by these things. So we're going to need to figure something else out. And the big idea behind this is to add some new points at infinity, because we have points everywhere else. So infinity is the only place to add them, where the lines do intersect. So here's the very cartoonish picture. I'm going to show a slightly more accurate mathy picture on the next slide, but it doesn't have a sunset. So this is a nicer picture. One version of our plane, which we kind of have grayed out right here, is we've got these 2 lines. You can think of them as, being railroad tracks that are always the same distance apart from each other, just going on forever and ever and ever. But if we now think of our plane lying flat and actually standing there and staring off into the distance as those lines go on forever and ever and ever, we see those 2 lines actually approaching each other, and it seems like they should be intersecting each other somewhere along that horizon. And if you drew more parallel lines to those, they would actually all vanish at the same point. And then if I had different parallel lines, they would go off and vanish at some other common point. So it seems like maybe there's going to be some way I can add new points at infinity. Okay. Yeah?
Multiple or just one?
Well, I think I want to add multiple. Because if I only add 1, then all the lines have to pass through that. And then that's going to be really weird if every line in the plane passes through the same point. I think that would lead to some weird stuff. We might run into problems like, I don't know, we might like any 2 points to define a line, right? That would be a nice property to hang on to as we're adding more points. So we're going to end up seeing that we're going to add more points. In fact, we're going to add 1 point for every set of parallel lines, basically to give them a place to intersect. Yeah. Okay. I think the next slide is maybe the most intricate, mathiest picture we got, but it's going to solve lots of problems for us. And so this is something called the projective plane. And all it is some way of adding in these points at infinity. So now instead of thinking of my points as just usual things sitting in a plane, my quote-unquote points are now going to be lines like this red line or this blue line that are passing through the origin in 3-dimensional space. So that's absolutely wild, right? We've left 2 dimensions behind. We're living in 3D space. I've got a point, and I'm looking at every line that goes through it. and that's going to be the set of points of my plane, that's absolutely nonsense. But I promise it's not actually, because let's suppose I had a plane hanging out at height 1, like this plane right here. Well, pretty much all of my lines pass through that plane at a single point, right? For example, this blue line passes through at that point, the red line passes through at that point, and so on. And so most of the lines I'm just going to identify as being points on this plane. And if you want, you can think of this line as just sort of being given by whatever direction it's heading in, an A, B, C. That's only defined up to scaling, because of course you could scale it by some non-zero number, multiply or divide it by something, and it's pointing in the same direction. So this is almost like we're taking whatever our direction vector of our line is and scaling it so that z coordinate's 1, so that you are sort of hanging out right there. So most of these lines you can identify with points on a plane. But there are some lines you can't. In particular, what if I had a perfectly horizontal line passing through the origin? It's never going to be intersecting that plane up there. And it turns out that those are the points at infinity that we're trying to add to our space. And indeed, if you thought about two lines running through that plane there, and this time I mean good old-fashioned lines, not lines through the origin, but lines living in that two-dimensional plane, if you think about the lines as points corresponding to those, in order for those to stay parallel in that plane, you would need those to get closer and closer and closer to each other as they sort of bent close to horizontal. And that's going to correspond to some point where those lines intersect. Very tricky, took me like 5 times seeing this to understand what the heck was going on. The algebra is actually surprisingly easy, and it's weird that you can make an algebra agree with all this, right? Because we did something weird to our geometry. Now we have to do something with our algebra. So for example, say we have these two lines, x plus y plus 2 equals 0, x plus y plus 1 equals 0. They're parallel, they're not going to intersect normally. We're going to make those polynomials homogeneous. All that means is I'm going to take a new variable, z, and throw it into any term that doesn't have the highest degree possible. So for example, there's a constant term, so it gets a z. There's a constant term, so it gets a z. Basically, you make it so everything's the same degree. And it turns out you can think about the set of points in this new projective plane that satisfy these equations. And there actually is a solution, namely if I let x be 1, y be minus 1, and z be 0, those two equations do have a common solution, which means those lines intersect at a point at infinity. There's a whole bunch of different ways of describing this projective plane, how you add those points at infinity, but the important thing is it makes it so that our lines are going to actually intersect at a point at infinity if they're parallel to each other. And much harder to visualize, but you can do this with any curves you want to, and importantly, you can kind of handle all the algebra any way you want to, or not any way you want to, but in a very nice, clear, explicit way. So here's now our falsehood-free, hopefully David won't catch me on anything again, Bézout's theorem. So let's let C and D be complex algebraic curves of degrees C and D with no common components. So complex meaning I'm going to work over the complex numbers. So I'm not going to lose any points by not thinking about that. I don't want any common components. That's to avoid silly cases where I've got line on top of line. I don't want that to be going on. Then C and D are going to intersect in C times D points in the projective plane, meaning I might have to have points off at infinity, as long as I count those with the correct multiplicity. So I had those curves barely touching each other, maybe that's going to get counted a whole lot more. At that point, we finally have a completely true theorem. By the way, fun fact about these circles, if you actually sit down with the equation of any circle and then do this homogenization trick and try to find where the points at infinity are, because indeed they are going to intersect each other at points at infinity, turns out any two circles pass through the same 2 points at infinity, which is just kind of wacky. It turns out circles are very, very special equations. So that's a whole lot of fun. So this is what Bézout's theorem looks like. That's the algebraic story. Next, we're going to get into the tropical world. Any questions on our algebra story here? Yeah, Mia.
Can you describe these 2 points at infinity?
Yeah, very explicitly. So if you, oh no, there's no chalk, mathematician's nightmare. So if you have, x minus a squared, y minus b squared equals constant, then homogenizing you just, oh, hooray! Thank you, Christina. So, assuming I can actually get this open, if we've got x minus a squared plus y minus b squared equals r squared. So we've got a circle of radius r centered at AB. Let's homogenize that. That gets a z, that gets a z, that gets a z squared. That's now homogeneous. Everything has the same degree. It's all degree 2 when you expand it out. The points at infinity, that's where we have z equal to 0. So now we set z equal to 0. Well, if z equals 0, lots of stuff goes away, and you just end up with x squared plus y squared equals 0. Now, normally, this would have one solution over the reals, 0, 0, and we don't actually allow that. That doesn't define a line in projective space. But if we're over the complex numbers, there are some points that satisfy this, namely 1 colon I colon 0 and 1 colon minus I colon 0, and any scaled version of those, but they're the same thing. So yeah, it turns out every circle you've ever met passes through those 2 points in the complex projective plane, which is just kind of wacky. I don't know, but circles are special. Any other questions? Okay, let's talk about tropical geometry. So tropical geometry is a piecewise linear version of algebraic geometry. I'm not going to go into all the foundational definitions and things like that, but I do want to give people an idea of what it looks like. These are going to be the sorts of shapes that we think about rather than those more curved curves from algebraic geometry. I think maybe there's one exception. I think this thing is what a tropical plane looks like in 3-dimensional space. So that's actually a 3D object, a tropical surface. These other ones, those are what tropical curves are going to look like. So somehow built out of straight line segments and rays and things like that, intersecting each other in all these intricate ways. And what I'll say is that these shapes are actually still defined by polynomials. So you still have this correspondence of I have some kind of nice equation, and I have a shape that it defines. The difference is, well, if you think about what goes into a polynomial, I'm adding stuff and I'm multiplying stuff. In tropical geometry, we're still going to add things and multiply things, except we're going to redefine plus and times. In particular, plus becomes min, so that 2 plus 3 is 2, because, you know, let's make arithmetic easier. And times becomes plus, so 2 times 3 is 5. And it turns out, bizarrely, if you treat polynomials with these new operations, these are the kinds of shapes that you're going to get. And you might think you're just going to get pure nonsense out. But it turns out you can get some really beautiful, really meaningful stuff. Before I get into the theory, though, of tropical geometry, there's a reasonable question that I think lots of people have, which is, why on earth would we call this tropical? And if you're very, very clever, you might think, maybe it's like polar coordinates. So some people may remember polar coordinates, which are a nice way of describing points in the plane based on an angle and distance from the origin, sort of what things look like near the North Pole if you're thinking about lines of longitude and latitude. And of course, it's not anywhere nearly as reasonable as that. The reason it's called tropical is because of this computer scientist and mathematician named Imre Simon. He was born in Hungary, moved to Brazil when he was quite young, I think, became a professor of computer science and mathematics at the University of São Paulo, Brazil, which you will note is very close to the Tropic of Capricorn. And so some mathematicians in the 90s were naming the field of tropical geometry, and he was one of the pioneers in it. And so what they ended up naming it was tropical. At first, I thought it was because they were saying, well, Brazil's in the tropics, let's just name it after that. That would be absolutely ridiculous because that's a huge part of the world and there's lots of mathematicians who come from there. And in fact, São Paulo is not in the tropics. It is south of the Tropic of Capricorn, not north of it. However, Professor Simon did live north of the Tropic of Capricorn, so he had to commute across the tropic every day going to work. There were probably some moments he was thinking about tropical geometry while crossing a tropic. So it's kind of stuck at this point, but that's why it's called tropical. So let me convince you in one slide that tropical geometry is not so different from regular geometry. Now, classically, 2 lines intersect at a point. Usually, I'm not giving you another certificate, David. I totally would if you caught me on something else. But usually, 2 lines are going to intersect at a point. That's also true tropically. So what does a tropical line look like? It turns out it always looks like a vertex with 3 rays shooting out of it, like this one, pointing in the plus x plus y and minus x minus y directions. Every tropical line looks like that. Most of the time, those are going to intersect in a single point. In fact, they always intersect at least one point. You can't have parallel tropical lines. They might intersect in infinitely many points. For example, you could imagine, what if I slid that down, then I'd get infinitely many points. So I have to worry about stuff like that. But, somehow it mirrors what we're used to happening in geometry. So maybe with some kind of fine print, I could get something like Bézout's theorem, right? 2 lines intersect at a point, 2 tropical curves with certain degrees should intersect a certain number of times. And in fact, there is a tropical Bézout's theorem. So what does tropical Bézout's theorem say? It says if I've got 2 tropical plane curves of degrees c and d, I haven't really talked about degrees too much, but remember, there's polynomials defining everything, so we still have degrees. Those are going to intersect in c times d points as long as we're willing to assume some fine print, just like we had to before. So in this picture here, I think we've got a degree 3 curve that looks, that's sort of colored in red, and then a degree 2 curve colored in black. And you'll notice those are intersecting in 2 times 3 equals 6 points, which absolutely matches this theorem. Now, oh yeah?
Do you mean times or times?
Oh, that's a wonderful question. The times, thanks Christina, the times that I do in the tropical world, I write like this. And the plus I write like that. So that is actual times. That is a very good question. But yeah, so times. So it's still the case that it's going to be 6 and not 5. It gets very intricate when you have all these operations flying around. And then you get max thrown in there, which is like plus prime, because it's kind of like plus, but different. Anyway, the sort of fine print we have to put into this is actually a lot less hefty than what we had to do with Bézout's theorem in the algebraic geometry case. In particular, okay, we again need to consider something about multiplicity. So for example, here is, it turns out a line, that's that shape in yellow there, and then we've got a purple conic, a purple tropical curve of degree 2. Those are only intersecting at a single point. However, there is a way in which we can count multiplicities that makes this make sense. It has something to do with what the slopes are at that point. In particular, if you like taking determinants of things, just take the determinants of the outgoing vectors. That tells you the multiplicity. That's actually a single point of multiplicity too. You also need to worry about this thing I mentioned, namely, what if your tropical curves are intersecting at infinitely many points? That's very easy to happen, right? Because they got all these rays and line segments. What if they overlap? For instance, here's 2 tropical lines that are intersecting along a long infinite ray. Well, I'm going to think of that as a single point occurring right there. And the way I do that is with the idea of stable intersection. All that means is I'm going to take one of my tropical curves, wiggle it a little bit, and you can prove that if you wiggle it generically enough, you're only going to have finitely many points. In this case, there's 1 point right there. And then start sliding them back together, sort of undo that wiggle. And then you keep track of where that intersection point went, and it's going to go right there. And you declare that to be your intersection point. And so in fact, you can even intersect a curve with itself, and it makes sense, because you could do a stable intersection there. And it turns out that that's all the fine print you need. You don't have to work over the complex numbers. We're still happy over just the reals. There's no need for points at infinity. At this point, we actually get Bézout's theorem completely. And I didn't put this on the slides, but one fun aside I wanted to mention is a natural thing to ask is like, well, okay, there was, algebraic Bézout's theorem. There was tropical Bézout's theorem. Can you take algebraic Bézout's theorem and use it to prove tropical Bézout's theorem? The answer is no, but you can do the other thing. In particular, if you're very careful, you can actually take a theorem like tropical Bézout's theorem and then prove something about how this governs the behavior of algebraic curves. Because there's actually a very strong relationship between algebraic curves and tropical curves. And in particular, the intersection theory of tropical curves tells you about algebraic curves. So it is very much not the proof that Bézout kind of didn't really write down. It's also not the proof that Sarah would have written down. But you can prove algebraic Bézout's theorem from tropical Bézout's theorem. And it's not hard to prove tropical Bézout's theorem. It's mostly drawing fun triangles and counting up some area. Proving that it actually implies the other one is some hard work, but sort of a fun connection between those two worlds. So what I wanted to do for the rest of the talk is highlight a couple of different other theorems besides Bézout's theorem that have a manifestation both in our algebraic world and our tropical world, just to give people a flavor of the sorts of things you can think about if you're doing tropical geometry. So for example, here's a beautiful theorem due to Plucker from 1834, a smooth plane curve of degree 4. So we haven't really looked at degree 4 curves, but this is a degree 4 curve here, made up of these 4 little, lima bean shaped looking things. It has 28 bitangent lines. What do we mean by a bitangent line? Well, if I take a line and intersect my curve of degree 4, it should intersect at 4 points, right? That's what Bézout's theorem tells me. Well, what if 2 of those points are points of higher multiplicity? What if it's like 1 point of multiplicity 2, another point of multiplicity 2? In other words, lines that just barely touch your curve at 2 points. Turns out it's kind of hard to find those. There's only finitely many of them. This picture, though, I think shows a total of 7 bitangent lines for this particular degree 4 curve, and you can actually rotate them to get a full 28. So very fun classical theorem, 28 bitangent lines for a smooth plane curve. You have to work over C, you have to work projectively, all the fine print from Bézout's theorem. Tropically, this was a theorem I proved with some folks back in grad school. A smooth tropical plane curve of degree 4, same basic setup, has 7 bitangent tropical lines. So somehow we've gone from 28 down to 7. Except not really. Technically, we have infinitely many. It turns out that this green line right here, that's bitangent to the tropical curve illustrated in black. And if I slid it around, it would actually still be giving me more bitangent lines. I actually have infinitely many, but they all kind of fall into a natural equivalence class. And you might notice, oh, well, there were 28 before, there's 7 now. 28 is divisible by 7. Is there some weird thing where your bitangent lines are collapsing in groups of 4? The answer is totally yes. We did not prove that. Some other people did after we proved this. But there's all sorts of other cool stuff that we got going on with these tropical curves of degree 4. Here's a very classical algebraic, well, very classical, early 1900s algebraic geometry problem. This was one of David Hilbert's 23 problems he posed, I think, in 1900. Qualitatively, this basically asks, what can an algebraic curve of degree d look like in terms of its overall quality and shape, not the precise geometry? So for example, I had a curve of degree 4 that looked like sort of 4 little blobs floating around here. You could also have a degree 4 curve that looks like 3 little blobs, or 2 little blobs, or 2 little blobs with one inside of the other, or one single blob. And it turns out I think that's all the things your curve of degree 4 can look like. By the way, this you really have to be working over the real numbers for, and I think non-projectively, for it to be an interesting question. So that's the sort of question that you can think about with Hilbert's 16 problem. It turns out this is unsolved even when you hit degree 8, so it's incredibly hard. So that's the answer for degree 4. Degree 6, very big answer, very difficult. Degree 8 is still open. There's a similar question that me and a lot of my collaborators have thought about, namely, what can a tropical curve of degree d look like qualitatively? So pictured here are a bunch of tropical curves of degree 4. These are the sorts of things we were talking about by tangents of a second ago. And how would I describe these qualitatively? Well, one of the things that stands out is they all have these 3 bounded regions. You can prove that's always the case. But the bounded regions relate to each other in different ways, right? For example, here I've got 3 bounded regions that all border each other. Here I've got 3 bounded regions where 2 of them border the third, but the first 2 don't border each other. Here I've got them more spread out, separated by these bridges, stuff like that. And so in particular, if I drew them in slightly more cartoonish ways, and this is me putting my graph theorist hat on, I would say this first one kind of looks like this picture here. Sort of this is the cartoonish picture of that. This one's the cartoonish picture of that, and so on. This is a cartoonish picture I might expect to see. It's 3 bounded faces. They're all kind of, satisfying the sorts of criteria these earlier ones did. But it turns out you can't find a tropical curve that looks like that qualitatively. That's something you can prove, but that indicates there's some very non-trivial stuff going on here. So this is a question I thought about during my PhD, also a question I've thought about lots since. In particular, 2 of my summer research groups, Small 2017 and Small 2020, thought about these things. There's some of the students I've worked with, including some thesis students. One of my current thesis students thinking about this, in particular about that last graph that didn't show up. Lots of fun stuff there. If you're curious, that Small was all on Zoom because it was 2020. They're currently trying to make a unimodular triangulation of a lattice polygon. One of those fun trends they learned from TikTok, presumably. So that's what we've got going on in that sort of problem. The last one I want to touch on, and this is going to be super, super broad, is a version of what's called divisor theory on curves. So divisor theory on curves is a really, really powerful tool in algebraic geometry. It tells you, given a curve in some kind of abstract way, what kind of spaces can I embed it into? What kind of maps does it have to other spaces? And what divisor theory kind of looks like is I have a curve, I've got collections of points on it, and maybe I mark them with integers, maybe 1, maybe you can have something marked more than once, maybe things get marked with negative numbers and so on, and somehow you define an equivalence relation between certain collection of points. So somehow that triple of points marked is equivalent to these points marked where that one gets marked with multiplicity 2. And there's a whole cool, beautiful theory behind those things in the algebraic world. The tropical version of that manifests as what's called chip-firing games on graphs. So you already saw where I took my tropical curves and simplified them down so they just look like little graphs. So vertices connected up by edges and things like that. That's sort of where this thing lives. And in particular, I'm going to think about placing some number of poker chips, let's say 3 poker chips on that vertex. And I'm going to follow certain chip-firing rules that let me move those poker chips around. And in particular, this placement of poker chips, it turns out, is related to this placement of poker chips. Basically, it has something to do with that vertex donating something to each one of its neighbors. And as we had in the case of Bézout's theorem, it turns out studying the tropical geometry down here, studying chip firing games on graphs, that tells you about divisor theory on curves. And there's actually some really beautiful cases where people have proved all sorts of open problems about algebraic curves using chip firing games on graphs. So this one I've done a couple more smalls on. I think there's small 2018, 2021, 2023. Whole lot of students I've worked with there. I think I'm going to have to invent a smaller font because I've got 8 more working with me this summer. But for now, this is all the ones I've worked with so far on that. And so obviously, as you can tell, these are great problems to work on with undergrads. And I'm very excited to have gotten to work with so many of them, supported in part by Williams, supported in part by NSF grants. So I'm sure you agree with me in thinking that, isn't it wonderful that we have funding to support wonderful experiences for students? So if you agree with that sentiment, you might be interested in going to the Stand Up for Science rally that's going on in Science Quad tomorrow afternoon so that, people can, try to keep promoting, great research experience for undergrads with all sorts of cool funding and things. And you can reach out to, I think, some of the folks in CompSci, Katie Rohit and Shika, if you want more info on that. So just to wrap up, there's these 2 worlds, algebraic and tropical geometry, both governed by different types of polynomials. They have very different looking geometries, but somehow they have all sorts of similar phenomena running around in those. Just to throw up some acknowledgments, again, all that's supported by NSF and by Williams. That font I was using on the title slide, that's this thing called Nullstellen font. It was invented by a couple students of mine as a final project. If you want to make your name be like a fun algebraic curve and find a polynomial equation defining something like that, you can check out that website there. Thank you so much. Questions? Yeah, Tom.
Is there a tropical version of the Schubert calculus?
I don't know. I don't think I know enough about Schubert calculus to know for sure. I see. I'm trying to think. I mean, I think a lot of tropical intersection theory is, a lot of it's quite subtle in terms of you want to define things in the right way that they keep having the right meaning when you lift things up to the algebraic world. And so I think things are often defined, with that in mind. So I'm not quite sure if all of that works out exactly the same way. I know there are instances where, something would be predicted to be a certain number, and that doesn't work tropically, I think. I mean, you could argue that the bitangent lines is exactly that. So if there is a version of it, it's going to be working a lot differently. It wouldn't surprise me if someone's tried that, though. I just happen not to know. Yeah, David.
So I have a sort of outside-the-box question, and hopefully this isn't one of the questions that you ask a mathematician. You say, well, there's an infinitely many number of these things. But, for you at least, that the tropical way of looking at things is particularly valuable and meaningful. And as someone who, has, learned it from you but hasn't seen it otherwise, like how many other types of things are there other than the algebraic and the tropical? Or is there something particular about this connection?
You mean like things where you have I don't know, where this is kind of like some kind of quantized, discretized version of what we had going on there? Or, I'm not sure. I mean, in general, it's always good if you can take what your problem is and reduce it to something combinatorial. That's not because combinatorics is easy. Combinatorics is very, very hard, but it's at least finite. So there's more ways of approaching that problem. So I think people are very excited when they can reduce things to that sort of world. I'm not sure if I know of that many instances where the relationship is as clean as between the algebraic and tropical worlds. There are also like intermediate states between these. So there's sort of, I glossed over, what the relationship between them is. Essentially, you can take a curve over your over the complex numbers, say, so your algebraic curve, and the way you turn it tropical is you take absolute values of things, you take logs of things, and then you take a limit. And in the limit, you get this tropical curve. If you don't take a limit, just take some absolute values, take some logs, and maybe take a little bit of a limit, then you get these fun shapes called amoebas, and so there's sort of an intermediate state between all these things. So that's sort of another world where you can kind of take something complex, hard to picture, and turn it into a real thing that has some nice convexity properties and nice combinatorics. But yeah, I don't know. I might not be thinking broad enough to be able to do a good job answering your question. Sorry. Yeah, Colin.
So, if tropical geometry had not been named after a latitude,
Yeah.
would it have been named discrete algebraic geometry?
I don't know. I don't think maybe discrete algebraic geometry would have been good. I feel people might have given it a boring name like max linear or min linear algebraic geometry. Because for a long time, the original motivation behind the whole min plus thing, some people do max plus instead of min plus, was basically doing linear algebra with those operations, because you can solve all sorts of things. So people were calling that stuff min linear or max linear systems. So somehow I feel min linear or max linear could have gotten put in there. Discrete algebraic geometry, you could absolutely, have called it something like that. I don't know what would have caught on. Tropical is admittedly a fun name, even if it's a very silly reason behind it. So I can kind of see why it stuck once people went for that, but yeah.
Yeah, so this is a question that doesn't have to do with the math, it just shows how ignorant I am what you do. But I'm really curious, you mentioned a number of times your collaborators.
Yeah.
And I'm wondering what the process of working on something like this with collaborators is like, whether it's people with other institutions or your students. I understand when a bunch of physicists are breaking down parts of experiments, but I don't understand how it works.
Yeah, so I can point to a couple ones. So obviously there's, working with students, in which case, it's very much, something like a 9-week program on campus, very actively collaborating with each other, daily or every other day, meetings with each other to come up with, new ideas, to report on what people have been trying out, figure out conjectures we think are true, attempt to prove things. So a lot of it's, just bouncing ideas off of each other and, collaborating with things.
Are parts of proofs,
They're parts of proofs, parts of examples, things that we think are true. Sometimes you have a theorem in mind and you're trying to prove it. Sometimes it's just, hey, here's a new question. What seems to be true? What happens when we tweak these things? Is there something nice and intricate there? And obviously, it's much more fun when you get to be in person. It's much harder once the summer ends and you still have to wrap up the paper and then you're emailing each other and all sorts of stuff like that. Another model, which is similar but in a much more compact way, was actually what led to this paper here. So this was done as part of what's called a math research community, which is a chance for grad students and postdocs or early career mathematicians to get together and work very intensely on a problem for about a week, and then hopefully have made enough progress that then they can maybe in their own institutions and emailing each other back and forth, try to turn it into a paper. And of course, that might involve getting to visit each other and talk problems through and all that fun stuff. So of course, you can, do a lot of this work remotely, as you say, splitting up these things into smaller pieces where one person tackles this lemma, one person tackles this proposition. It is just so much easier and much more fun when you're with them and talking through. And, this is one of the big reasons why we like to go, give talks at our friends' institutions so that we then have a chance to be like, okay, let's try to hammer out the details of this thing.
Is there anything else besides min plus that works as a nice way to define polynomials?
Technically max plus, because it looks like the same thing but upside down. So I'll even argue there's ways in which it's not so nice. So the thing that makes min plus kind of work but not work quite as well as our usual plus times is that plus times gives us a ring, which means we can add and multiply things and everything works the way you think it does. Now, of course, you have to write down a big list of what the we think it does means, but for instance, addition and multiplication play nice with the distributive law. I can, expand things out like that. That's also true for my plus and times, for min plus and also for max plus. I have to throw a few things in there. Maybe I want infinity to be my additive identity and stuff like that. The big difference here is you can't subtract stuff because 2 plus 3 is 2, and you can't add anything to it to get back to 3. And so this sort of structure is what you call a semi-ring rather than a ring. And when you lose that, a lot of the theory that goes into making rings work so well, which is a lot of what goes into understanding algebraic geometry, that makes things a lot harder. And in fact, a lot of the work that, for example, Professor Lepp does in terms of studying ideals in rings, that's much, much harder once you move into semi-ring world. It's not even obvious what the definition of ideals should be. If you copy-paste your definition into the tropical world, you get a very, very bad thing. So it's sort of a miracle they work as well as they do, I think. But yeah, in principle, you could be thinking about this for other rings or for other semi-rings as well. Yeah. Other questions?
What do you do when you're trying to translate into tropical form something that has a subtraction in it? Does that also get min?
Yeah. So just to throw out an example, I didn't include this on the Thanks, Christina. I didn't include this on the slide, but if you did something like, x squared plus, a times x plus b, say we had, a tropical quadratic polynomial right here, it turns out the points you think about, if you graph this, let's see, I'm doing min, so if I'm doing min, it's going to go like this. The graph of your function looks something like this. There's sort of a point where that x squared is kind of like 2x. And so when that's the min, it's like that kind of slope. And then that's the min, it's that kind of slope, and so on. So you do have these things called tropical roots, which are the points where those bends happen. That ends up being more interesting than crossing the x-axis. So what you'd like to say is this should be able to factor as x minus alpha times x minus beta. But we can't because there's no minuses. Well, plus is pretty close to being a minus, right? So we'll do plus, and miraculously it works. And in fact, there is a reason behind that. There's another way of tropicalizing things called taking valuations, and valuations don't care about plus and minus. So essentially, the minuses do become plus as well. This manifests in all sorts of fun ways, like say you're trying to do tropical linear algebra. Well, a lot of things don't work anymore because when you're simplifying a matrix, one of the things you love to do is subtract a multiple of one row from another. You can't subtract things anymore, so you're in trouble. And then how do you define a determinant? Determinants have minus signs in them. Just make them plus signs. It's probably fine. So there's all sorts of funny things where sometimes you really have to worry about not having minuses, but sometimes it works out. Sort of funny. Depends on the context.
Okay, thanks everyone for joining us today. Let's thank Ralph again.
Thank you so much.